Okay, so let's start. I hope you all had a good Thanksgiving. So now we are at the what's happening? Okay. Okay. Not sure what's going on here. No, it's this. It's I'm using VGA, which.
Yeah, but I think it's the order when I was told one at the same time. So like put that adapter in first.
No.
Plug it in now.
restarting might do it, but it's not that. It's just that something is flaky here. Sure. Okay, so it decided to update something. Sorry about it. Anyhow, so there were two administration slides that I can talk about without it. So one, surveys. About 35% of you did the surveys, maybe 40%. I want to get to 80%. So please, please do the survey. Wouldn't take more than 5 minutes of your time. Maybe 10 minutes if you take it really seriously. So please do it. It's informative for us. Will help both you and your friends when they take the class in the future. Okay, we'll try again. Okay, let's hope that, so surveys, I talked about projects. I still haven't seen all the people that are doing projects. It's getting close to the end, so please come and talk to me. Posters for the project, as we said on the website, will be presented in the last meeting of the class, which means 2 weeks from today, I think, December 10, during the class time. We don't have a final place where this will be, but we're gonna give you instructions on what to do, where to do it. The final report, on the other hand, we're gonna give you a lot more time, so it will be only due after the final December 18. And again, we'll give instructions. In fact, it's already on the web. What we expect from a final report, ask questions if you have any. Okay, homework. As you all know, homework 4 is out now. By the end of today, you should know everything that is needed. As you probably observed, we had some problems with the embarrassing problem with the template LaTeX. We fixed that, which means we changed a little bit one of the last problem. Hopefully no one has solved it already, and if you have, it's going to be easy for you to solve it, the new one. Okay, finals. You probably want to know, it's based on the university schedule, it's going to be December 17. I can't remember the time, but it's in a big room, so it will not be as dense as the midterm was. It will be the same in terms of structure as the midterm, but there's going to be a lot more time. It's going to be 2 hours. And the one important thing is, for you to realize it's structured the same, it covers everything we've done, with slightly more emphasis on what we've done since the midterm. Everything we did in class and in the homework is going to be or could be in the final. Things that are in the slides, but I said I'm not going to talk about it, are not in the final. So for example, we talked about boosting, which means boosting epsilon, the error. There are slides on boosting the confidence. We don't care about it. I didn't talk about it. We talked about multi-class classification, one versus all versus all, but we didn't talk about error correcting code. We didn't talk about constraint classification. They are not in the exam. We will give practice exams, and the last homework will also be partly at least preparation for the exam. It will force you to look at all the material or large parts of the materials. Final comment on this, which is in fact a response to some comments or questions that people ask in the surveys already. So the class is applied machine learning, 2 colors, right? And the idea is that we cannot ask everything in any way. So the exams are mostly about understanding machine learning. You don't want to be asked to program in the exam. And the homework is mostly about the application part because that's where we can do it. Altogether, each one of them, altogether they cover 100%. Each one is about 50% of your grade. For people that are not doing project. If you're doing project, the balance changes a little bit. Questions? Yeah. I don't remember the time here, but it's it will be on the web, and we'll announce it. Yeah.
Are we going to be expecting the same number of questions for the time that is extra, or are you going to?
Yeah, it will be about the same length, at least. We are going to think, coming in, that it's about the same length. We'll see. Other questions? Okay, so let's move back to where we are. So we are talking about Bayesian learning. People that were not here on Wednesday hopefully have already watched all the videos. And know everything, but I'm going to remind you where we are. So we're talking about Bayesian learning, probabilistic learning, which means that everything we are doing is basically using this very simple formula, Bayes rule, that is up here. We care about a hypothesis H, and we are given data D. And P of A, and we want to compute the probability of H given the data. This is what we call posterior distribution. And Bayes' rule says that it's given as the probability of the data given the hypothesis times the probability of the hypothesis divided by P of D. This is nothing more than the product rule in probability written by isolating P of H given D on the left. So H is going to be a member in a collection of candidate hypotheses, and we try to find the most probable one. The way we're going to do it is we're going to argmax over all members of capital H, as is illustrating here in this rectangle. So the maximum posteriori hypothesis is argmax over all possible hypotheses of P of H given D. I'm placing here Bayes' rule, and noticing that when I'm doing argmax over all members of H, I don't care about the denominator here, so I can just do argmax over P of D given H, P of H. That's it. Everything we're going to do, everything that Bayesian learning is written here. The only differences are how do we choose H, and what is the probabilistic model that we are assuming over the H's. That's it. Other than that, it's just instantiating into this Bayes rule. So And we gave a lot of examples. And I'm going to just quickly remind you. One example that we gave was this one. So we have a coin. We toss a coin. And we know that there are two possible hypotheses. Now, hypotheses can be many things. And we're going to see that more today. Hypotheses could be outcomes. Hypotheses could be parameters. Hypotheses could be functions. In this case, the hypothesis is a parameter, the bias of the coin. Is it a fair coin, 0.5, or is it a biased coin, 0.6 for heads? And what we've done is we started with these two options, and we used Bayes' rule. Essentially, we added a prior. We think, coming a priori, without seeing any data, that H1 is a lot more likely than H2. And we also looked at data. We tossed a coin. And from that, we can compute what is the a posteriori hypothesis. And you can go over this and see it. So we also did it for the case of 100 coin tosses. And then the more interesting case that we've done is this one. So in the first example, all I had was two hypotheses. Finite hypothesis space. I can just try it for the first hypothesis, compute its probability, its likelihood. I can try it for the second one and see which one is larger. In this case, when I toss a coin, the real case of tossing a coin, I have infinitely many options for the bias of the coin. It's P ranges from 0 to 1. And again, I'm going to use Bayes' rule. And magically, we got that P is indeed, as you would guess in this case, M over K. K over M, sorry. M trials, K heads. And the reason is that we made a specific assumption on how the data is generated, and we assumed it is generated with the binomial distribution. That's an important assumption. You could have assumed a different model. In fact, in the homework, you would have assumed a different model, and you'll see that just observing a specific sequence does not necessarily mean that you take the number of heads divided by the number of tosses, and you get the number. So it really depends on the model you assume. Okay, so we played with a few more examples. I also gave examples of probability distributions. Hopefully all of you have seen that, Bernoulli distributions, binomial distributions. That's one pair. A second pair was a pair of categorical distribution. Think about throwing a die. And multinomial distribution, which is you're tossing multiple dice. Hopefully you've seen this. If not, look at it carefully and make sure that you understand what happens when you use a dice. And then we got to the next example, which we finished with last time, and I want to go over it again. Questions so far? Okay, so okay, 1 second. So we are given a collection of documents written with a vocabulary of 3 words, A, B, and C. All the documents have exactly n words. Each word is either A or B or C. And our goal is to decide whether a document is good or bad. So documents come to us labeled as good or bad. Something happened to my animation here, but this is our eventual goal. Given a document, predict whether it's good or bad. Now the question for us is, how do we make this a learning problem? A week ago, you knew how to make this a learning problem, right? So you would just take these examples. You're doing it, you've done things like this also in problem sets. You take the set of examples that are labeled, you extract features somehow, and you throw it into your favorite classifier. Now we are going to play a slightly different game. When we model it, we really have to think, what is now the learning problem? And the learning problem is going to be driven in a slightly different way. So the model that we are playing with now is called the generative model. That is, we are imagining a way in which these documents were generated. It's some parameterized way. And then we're going to use this way in which it's generated to estimate the parameters. And now we know everything about the problem. So what is our generative model? We assume that it generates document in the following way. First of all, it decides, am I going to generate a good document or a bad document? With probability eta here, I'm generating a good document here. Once I decided which document to generate, I'm generating the document. So I'm placing the A, B's, and C's into the document. So I'm going to generate AIAs, BIBs, CICs into the document. That is the sum of AI plus BI plus CI is n for each I, for the ith document as n words. And how exactly do I generate it? Using multinomial distribution, which means that the probability of a specific document, di, given that I decided it's a good document, y equal 1, is this, n factorial divided by ai factorial, bi factorial, ci factorial. This is the constant that the multinomial distribution comes with, times alpha 1 to the AI, B1 to the BI, gamma 1 to the CI, where alpha 1 is the probability of generating an A, beta 1 is the probability of generating a B, gamma 1 is the probability of generating a C in a good document. Okay? So again, first of all, I decided which document it is, which type of document, good or bad. If it's good, which happened with probability eta, I'm deciding with probability alpha 1, beta 1, gamma 1, whether it's going to be an A or a B or a C. That's it. And therefore, once I've seen this document and I know that it has AIAs, BIBs, CICs, that's the probability of this document. And similarly, that's the probability of observing a document if its label is 0. The same thing, only that now my parameters are alpha 0, beta 0, gamma 0. And of course, the sum of alpha 0 plus beta 0 plus gamma 0 is 1, and the same thing for those that have 1. Yes?
So is the model here, like, it's generating by effectively pushing like a three-sided die?
Yeah. Yeah. You can think about it this way, right? It's a three-sided die that decides whether it's an A or a B or a C, and it's doing it n times. So that's how a model is generated. And now, and this is really a multinomial bag of words, because I assumed that the person who generated the document used the multinomial distribution. Now, I know that. That's an assumption. What I don't know is exactly what are the parameters this guy used. And this is my learning problem. So my learning problem is going to be, once I agree that these are my assumptions, multinomial with these constants, I'm going to observe a lot of documents, and I'm going to estimate the parameters. Once I know these parameters, when you give me a document, it's easy for me to compute what's the probability that it's 0, what's the probability of it's 1. It's just written here, right? If you know these alpha, beta, and gammas, you can compute these two numbers, compare which one is larger, and you can make a prediction. Okay? So is it clear what is the learning problem here? Other questions? Okay, so again, this is the generation. And once we generate, we have a classification problem. Let's be a little bit more specific. I'm not sure what's going on here. 1 second. Okay, so the question for us, let me just do something just a second. Okay, so the question is, how do we estimate these parameters? That's the problem that we have. The goal is to compute the most likely value of the parameters, exactly the same thing that we did for the coin toss, only that now the model is a little bit more sophisticated. So I'm going to compute the probability of the data. What is the probability of the data? Is a product over all the documents I've seen product over all I. My assumption is the documents are generated independently. So it's the product over all I, P of y, comma, di, which is equivalent to writing it this way, P of di given yi times P of yi. I denoted P of yi as eta, and I computed an expression for P of di given yi. And now I'm going to write now the probability of the data. Now notice that I don't know when I'm writing this, when I'm writing P of yi, comma d, I don't know what is the value of y. The way you really want to write it is, if y is 1, write the probability this way. If y is 0, write the probability that way. You agree? If y is 1, you want to use the alpha 1, beta 1, gamma 1. If y is 0, you want to use the alpha 0, beta 0, gamma 0. But I don't know when I'm writing this expression, the algebraic expression, which one I'm going to use. So what I'm writing here is a trick that will allow me to write both of them together. So here is what I'm doing. On the left side here, I'm writing the probability as if it's the one value. I'm using alpha 1, beta 1, gamma 1. On the right side here, I'm writing the same thing with the alpha 0, beta 0, gamma 0. Let's look more carefully at this. This is the probability, it's eta, the probability that y is 1, times the constant that has to do with ai, bi, and ci's, times the probability alpha 1 to the ai, beta 1 to the bi, gamma y to the ci. Now, I'm taking all this to the power yi. What does that mean? If yi is 1 indeed, then this expression is going to just sit there. It's going to be this expression to the power 1. If yi happen to be 0, then it's to the power of 0, which means this expression actually becomes 1, it disappears. Similarly here. Here I'm writing the case of y equals 0. So py is 1 minus eta times the constant times the probability with the zeros, alpha 0, beta 0, gamma 0, to the power of 1 minus yi. So if yi is 0, that means that the power here is 1, and I just see this expression. If yi is 1, then this becomes 1, all this expression, and basically disappears. So this way I've written at the same time the product of that takes into account both options. Okay, so that's an important trick. It's not the only way to do it. I could also write it additively, but I want to write it multiplicatively because I'm going to use logs later on. Okay, So now I want to maximize it with respect to each one of the parameters. First of all, as I said, I'm going to compute the log of the likelihood. This is convenient both computationally. It's easier to differentiate. It's easier to deal with logs. And also, as I mentioned already last time, numerically. So when you do your homework 4, you want to work in the log space, because otherwise, when you multiply a lot of probabilities together, very quickly it becomes 0. If you work in the log space, you can compute. So what happens when we move to the log space? Simply, these powers go and become coefficients. So I'm going to get yi times log of eta, some constant which comes from this product here of the ai, bi, ci's factorials, plus this expression over the alpha 1, beta 1, and gamma 1. Similarly, I get the same thing with coefficient 1 minus yi and log of 1 minus eta, and the alpha 0, beta 0, gamma 0. So that's the log. Now I want to differentiate it with respect to each one of the parameters and find the most likely value of the parameters. So I'm going to do here it relative to eta. And if you do a little bit of algebra, everything here is going to disappear. Everything here is going to disappear. All I'm going to stay is with these two components, which means I'm going to get yi over eta minus 1 minus yi over 1 minus eta. I want this to be equal to 0. And if you equate this to 0 and do the algebra, you'll quickly get that eta is this, the sum of all the yi divided by m. Does this make sense? Why does it make sense? Why is that your expectation for the value of eta? What does it mean, sum of yi divided by m? What portion of the document? It's exactly the portion or the fraction of the good documents. For a good document, yi is 1. For a bad document, yi is 0. So essentially, the numerator there is the number of good documents divided by m. You want this to be eta. Okay? So we got something that is sensible. Everyone agrees? And if you do the same thing for the alpha, beta, and gamma, you will also get things that are sensible. One warning sign, if you're doing it, you have to make sure that you realize that the numbers are not independent. The parameters are not independent, because alpha 0 plus beta 0 plus gamma 0 has to be 1. And the same thing for the ones. So in fact, it's sufficient for you to compute 2 of them. Okay, so that was a more sophisticated example. I'm going to give one other example before we move on. And the example is that of another generative model. It's called HMMs, or for hidden Markov models. Again, the point I'm trying to make is that it's actually very simple. Once you imagine the generative model, you can write the likelihood, and from that, you compute. So everything is really one basic rule and a lot of different instantiations. So what is this specific model that we're talking about now? You can think about it in 2 different ways. Think about taking a sentence and chunking it into phrases, where you have 2 states. B is the beginning of the phrase, I is inside the phrase. Or you can think about going into a room. You go into one of 2 rooms. One of them is called the B room. Another one is called the I room. And when you are in the B room, you observe something, an X. When you are in the I room, you observe something else, another X. And potentially, there are different probabilities for observing different X's, depending on whether you're in the B room or the I room. Or similarly, in the chunking case, if the word that you observe, if you're at the beginning of the phrase, or the words that you could observe, have a different distribution than words that you observe if you are already inside the phrase, not in the first word of the phrase. So how do we model it? We can think about starting at state B, and when we are at state B, we produce something, we observe an X with some probability, P of X over B, given B, and then we decide whether we're going to stay in B. With probability 0.8, we're going to stay at B. With probability 0.2, we're going to move to I. Once we are at I, again, we observe X with probability P of X given I, and we can decide whether we're going to stay in I, probability 0.5, or move back to B. That's it. So that's the model. So this model produces a sequence of X's. My X's here are taken from the vocabulary of A, B, C, D, E. So in the output, you're going to see A, B, C, D, E. But the way it was produced is what was produced by you visiting these two rooms in some sequence. It's called hidden Markov model because typically you are not going to see which rooms you visited. You're just going to see the observation, the X's. Or you're not going to know how the sentence is chunked into pieces, but you're going to see the words. Okay, so what are the parameters of these models? In order to generate this sequence of observation, you need to know what is the probability that you're going to start in B or in I. In this case, I'm suggesting that we always start in B. So P of B is 1 and P of I is 0. That's the initial probability. And then you need to have transition probabilities. What is the probability of moving from one room to another? So we have to have probability of moving from B to B, from B to I, from I to B, from I to I, which are written in these 4 parameters here. And then we have to have output probabilities. Given that you are in B, what is the probability of A? What's the probability of B? For C, and so on. Given that you are in I, what's the probability of producing or observing A, B, C, and so on? 5 numbers here that have to sum to 1 in each row. Once I have this, I understand the generation process. You can think about it this way. This is an alternative way to the picture that I drew here. You can say, okay, I'm starting in B. I produced A. And then I moved to I. I produced C. I moved to I again. Or I stayed at I. I produced D. I stayed at I, produced A. And then I moved to B, produced D, and so on. So that's the sequence. This is what has happened. And the sequence of observations is this, A, C, D, A, D. So this is a generative model, and what you're seeing here is the output of a generative model. It's a very useful generative model. It can be used to model many things. I just used it here to model 2 problems, 2 very different problems. What are the computational problems? It's exactly the same computational problem that we've seen before. So we have data. The data is a collection of observation x1 up to xm, and potentially the states, the I and the B's, S1 up to Sm. So it's going to be hidden if I'm not going to see the sequences. But at this point, everything that we're doing is supervised. So I'm showing you the data, the observation, and the labels. Which rooms have I visited, the S1 up to Sm? And my goal is, under the assumption that this is how the data was generated using this hidden Markov model, find the most likely parameters of the model. Find the P of S1, the P of Si plus 1 given Si, and the P of Xi given Si. Now, and I'm going to do this using Bayes' rule. And in the future, given an unlabeled example, an observation, just the x1 up to xm, my goal is going to be to predict the most likely label, S1 up to Sm. Yes.
Is it 2 to the m because it's 2 states?
Okay, I didn't get to it. So first of all, the question is, this is the goal, right? So this is the prediction problem, right? Similarly to what we've done before when we wanted to know whether the document is good or bad. In this case, once I see the x1 up to xm, I want to predict s1 up to xm. And that's how I'm doing it, right? So it's the argmax over all possible labels, P of L given x, which Bayes' rule says is this. So until here, everyone should agree. That's just the prediction problem. Find the most likely S sequence given the X sequence. Now, let's think about the hypothesis space that we have here. When we tossed the coin first time, we had two hypotheses, 0.5 head, 0.6 head. When we tossed the coin in the second example, we had an infinite hypothesis space, but continuous, so we can differentiate to get P. In the previous example of the document, we had two hypotheses, or 7 hypotheses, right? Parameters. But again, we can differentiate 7 parameters, each one of them continuous, so infinitely many options for each one of them, but again, we could differentiate. In this case, how do I compute? Let's assume that I already computed the parameter of the models. It's just like the problem before. So computing the P of x given S, P of S given S, Si plus 1 given Si, P of S1, this is a very similar problem if I'm supervised to the coin problem, right? So I'm looking at all my examples, and I'm looking at what was the initial states. If I see 100 examples, and in 30 of them, B was the initial state. In 70 of them, I was the initial state. I know that P of I, under the assumption of binomial distribution, P of S1 being Y is I is 0.7. Okay? So I know how to compute these parameters. But the question is, how do I make the prediction here? This is where the computational issue comes in. I have to do argmax here. Okay, and argmax over the sequence. How many possible sequences are there? And this is where your question comes in. So if I have m states, and each one can be B or I, there are 2 to the m possible sequences, and I have to choose the most likely sequence. Now notice that the states are not independent, right? So if in a time 7 and I equals 7, I'm in a specific state, the state I'm in at time 8, I equal 8, is not independent. So I cannot, so I really have to look at the whole sequence. And in principle, I have 2 to the m sequences, so computing the argmax here is going to be, in principle, difficult. Now, there are efficient algorithms to do it. Because this is a hidden Markov model, you can actually use dynamic programming and compute this efficiently. But in principle, the space that you're at is of size 2 to the m.
If there were 3 states, it would be 3 to the m.
Yeah. Just think about how many sequences are there, right? So it's the size of the alphabet in each position to the power of the length, right? Okay, so again, I gave this mostly as an example of the game we're playing here, which is you have to make an assumption on how the data is generated, and this is where the assumptions are. And then you observe data, and once you observe data, you're able to compute the parameters. So you have a family of models that could have generated the data. Once you see data, you nail down one specific element, one specific function in this collection. Questions? Okay. So far, we've given examples of Bayes, using Bayes' rule in multiple ways. That is, the H could be different things. In principle, H could be a collection of functions. In principle, H could be just a decision. And we can be Bayesian with respect to each one of them or all of them. The important thing to understand is that what you decide H to be, capital H to be, is important because different decisions will result in different outcomes. So let's give an example of that. So in all cases, we're going to do this, but we can either choose a function and then use it forever, or we can say, I'm going to be Bayesian about the prediction, and I'm going to not make a decision on the function. So let's take the following example. So let's assume I have 3 hypotheses. And given the data, H1, and the probability of, the priors over them are H1 has a probability of 0.4, H2 has a probability of 0.3, H3 has a probability of 0.3. So if I have to choose the hypothesis, I'm going to choose H1. So let's assume I chose H1, and that's it. From now on, I'm going to use H1 because this was the most likely hypothesis. And whenever you give me data, I'm making prediction based on this H1. Here is data. On this new instance X, H1 says 1, H2 and 3 say 0. Nevertheless, I'm using H1, so I'm going to make a prediction of 1. On the other hand, I could have said, you know what, I'm not going to make a decision on H's. I'm going to hold my breath, and I'm going to make a decision only after I see the data. So what would that be like? So I'm going to keep the probabilities over the H's, H1, H2, and 3. I will not commit to a specific H. And only after I see X, I'm going to weigh in the probability over the H's and make a decision. So you see, it's going to be different. Hopefully you can see already. But it requires that I'm going to keep more information rather than making a decision on the H's and then forgetting about it and working only with H1, which was the most likely hypothesis. I'm going to have to keep the distribution over the H's. And if I do keep the distribution over the H's, what do I get? So let's assume that I have a set of possible classification, V, capital V. So now I'm going to make the decision in the following way. The probability of V, given the data, is going to be the sum over all the H's, P of V given H and the data, P of H given D. So what I've written here is just the total probability formula, which you've seen, right? So the probability of V given D is the sum over all H's. I'm conditioning on H. P of V given H and D times P of H given D, right? So this is something that is always true, and you should feel comfortable writing this. Next is something that is not always true. So I'm replacing P of V given H and D by P of V given H. But this is also okay in this case, because given that I know H, the data doesn't matter anymore, right? I know H, so I know what's going to be the value of V, right? So I can replace this expression with this one. And this is how I'm going to make predictions, okay? This is just to highlight that these two are the same. So my base optimal classification then is going to be the argmax over P of Vj given D, which is argmax over all the VIs of this expression, which I now derived. And let's do it now in the case of this example. So in the example, the probability of Y given the data is the sum over all 3 hypotheses. Hi ranges over the 3 hypotheses that we had, H1, H2, H3. P of 1 given Hi times P of Hi given the data. And remember that we had 1, the H1 says 1, and H2 and 3 said 0. In this case, I'm going to get 0.4 here. And the same thing, the probability of 0, again, I'm summing over all the H's. H1 with probability 0.4 said 0. H2 and 3 said 1. So in this case, I'm going to choose to predict 0. So again, the important thing here is that I decided how to implement my being Bayesian in 2 different ways. In the first way, you can think about it as some kind of a pipeline process. I made a decision in the first stage. I committed to an H, and from that on, I'm just evaluating it. In the second stage, in the second way, I maintain a probability distribution over all the H's. It's more costly, but I can make better decisions. Okay, so why is this important? That's important because now we want to use similar principles in the context of classifications. And we're going to talk about perhaps the most important concept or algorithm in this part of the course, which is a Bayesian classifier. With some assumption, it will become the naive Bayesian classifier. So what is my goal? My goal is to make predictions over a finite set of values V, given instances that I'm going to assume for now, for simplicity, are Boolean features. X is x1 up to xn, xi is Boolean. Given an example, I want to assign it the most probable value. So how do I do it? So Bayes' rule says, if you want to find the most likely V, do argmax over all possible values of V, of P of V given X, and I'm going to write it down. X is my x1 up to xn. So Bayes' rule says if you want to compute P of V given X, compute P of X given V times P of V divided by P of X. That's just Bayes' rule. I don't need the denominator, so I'm rewriting it as argmax over all possible V's, P of X given V times P of V. Okay? So far, nothing happened beyond the same Bayes' rule that we used before. And I'm reminding you a convention that I'm using all the time. When we say P of Y or P of Vj, for example, what we mean is P of Vj taking the value Y, or P of Y given taking the value Y. Okay, so now that I agree that V map is this argmax over all V's, P of X given V, P of V, I want to make this more concrete and figure out, okay, so when you give me data, which parameters do I need to compute in order to make these predictions? So estimating P of V is easy, right? Well, I'm assuming binomial distribution, so I'm going to look at my data and count of all my data items, how many of them were labeled V. And this fraction is going to give me P of V. What about P of x1 up to xn given V? I can do the same thing, right? Any problem, potential problem. So what is this x1 up to xn? This is the example that you see. It has n features, if you want. And I want to know what's the probability of this example given that the label is 0, or the label is 1, or the label is 2. Yes?
So I would assume if you have like multiple labels and you don't have a lot of data points, then many of those values do not exist, or like all the values of V for all the classification.
So the problem is exactly that the instance space, x1 up to xn, could be huge, right? If n is 100, it's 2 to the 100 instances. You will never see them. You will see a very small, a tiny fraction of them, which means if you just go by counting, this number will always be 0. Okay? So just computing this in a straightforward way is not going to give me any reasonable way of estimation. So here is where I need to make some assumptions because I'll never see the data. So in order to use a Bayesian classifier in practice, we have to make the assumptions on the data so that we can estimate the parameters. So in the naive Bayes classifier, we're going to make very specific assumptions. Before we get to the assumptions, I'm going to rewrite this a little bit. So I'm rewriting P of x1 up to xn given Vj. And everything I'm writing here is always true. There's no assumptions here, right? So I can write it as P of x1 given x2 up to xn and Vj times P of x2 up to xn given Vj, right? So here, I didn't do anything, right? I just rewrote it. Everyone should agree that this is the same. If not, convince yourself. And I can continue. So I just copied the first one here, and I took this one and I wrote it as P of x2 given the rest and Vj times P of the rest given Vj. Again, no assumption. It's always true. And I can keep on going, and I get to this product. Basically, I decided on an ordering of the variables from x1 to xn, and then I can always write this. And now I'm going to make an assumption. And the assumption is going to be that the feature values, the xi's, are independent given the target value. With this assumption, I can write this now as P of xi given product of P of xi given Vj. So what does that mean? It means that P of x1 is independent of x2 up to xn given Vj. So I can write this expression as just P of x1 given Vj. It means that x2 is independent of all the other xi's given Vj, so I can write it as P of x2 given Vj. And the same for all the others, so I'm getting this product. So that's the naive Bayes assumption, conditional independence given the label. Okay, so what does that mean? So now what I got, given this assumption, is a very simple model that is very easy to estimate. In order to estimate what's written there at the top, P of x1 up to xn given V times P of V, all I'm going to estimate is instead of estimating this, I'm going to estimate P of xi, this should be a subscript, equal bi given the label, and I'm going to multiply all of them, I equal 1 to n. So essentially, what's happening here is a generative model where what I'm assuming is that the data is generated in the following way. First of all, I'm choosing the value, the V, the label. I'm choosing it according to P of V. Once I decided, I'm choosing each one of the xi's separately because they're independent given the value Vj. So I'm choosing x1 given Vj according to the probability P of x1 given Vj, x2 given Vj according to this probability, and so on. So you can think about it in a very similar way to what I've done with the documents, only that here I'm choosing features given the label. Okay, so let's summarize where we are. Okay, so I want to compute V maxima posteriori, which is this argmax over all possible labels of P of X given V times P of V, and I'm doing it by decomposing P of X1 Xn given V to this product of P of Xi given V. What does that mean? It means that what are the parameters that I have to learn? Let's assume that size of V is the number of possible labels. So I have to estimate size of V numbers here, and I have to estimate n times size of V for these. Let's look at it here. So V parameters here, and n times V parameters here. Everyone agrees with that? Okay. So, so that's the learning. If I want to make prediction this way, I'm going to estimate this V plus n times V parameters, and that's it. Now notice that this is a very different learning methods than what we've done so far. Right? It's not error-driven. All I'm doing here is I'm looking at the data, I'm computing V plus NV parameters, and that's it. It's directly from the data, no error-driven. I don't know how well it's going to do on the training. I don't know anything. I just believe something. I believe this generative model, this assumption, and under this assumption, I'm going to compute a predictor and use it. Why does it work? Assuming that it works. It's actually a very good classifier. Very simple, but very good classifier. Any reason it should work? Or any cases where you think something like this would work? So what happens if these assumptions that I'm making here, the conditional independence assumptions, are correct? Would it work? Then it should work. In fact, if the conditional independence assumption work, then it should be the best classifier, right? Because it's the most likely value, the most likely label. So the problem is that these are very strong assumptions, and in general, they will not work. So the question is going to be, why would it work even when the conditional independence assumptions aren't working? Think about data that you've played with already. To what extent you believe that the features are conditionally independent given the label? So you're playing now with documents. Yes? Yeah, I think in almost all data that you look at, they are not. Now, there's one important thing to notice, and it's going to be on the next two slides that I'm not going to read very carefully. Look at it. It's important to realize that conditional independence is not the same as independence. So in the next two slides, what I'm showing is that these two types of independence are actually two different types of independence. So two variables can be independent, but not conditionally independent. and two variables can be conditionally independent, but not independent. So there are just two different conditions. But either way, the conditional independence assumption, if you think about it, of your features is a strong assumption. So instead of doing this, let's take an example. So this is an example that you've already seen. It's the tennis playing that we played with at the beginning of the semester when we did decision trees. Same data sets, 14 examples, and now we want to use naive Bayes to do it. So what are we going to do? So we have these 14 examples. We have 4 features: outlook, temperature, humidity, wind, one label, play tennis, Boolean, and we want to do argmax over the two values, P of V, given this product. And the question is, what parameters and how do we deal with it? So let's just run the naive Bayes algorithm on the slides. Everyone is with me? Okay, so we have to estimate our parameters. Eventually, we care about the probability of the observation given V. And these are the parameters that we have to compute. So first of all, at the top, we have to compute the probability of V. It is P of Vj. So it's the probability of play tennis, probability of don't play tennis. Anyone remembers what the numbers are? What are these numbers? You can count. I want to know what's the probability of the label, P of V. There are two numbers.
Yes, it's 9 over 14 and then 5 over
9 over 14 and 5 over 14, okay? So that's one set of parameters I need to compute. The second set of parameters I need to compute is for outlook. Outlook can take these values, sunny, overcast, raining, and I need to compute this given yes and given no. So altogether 6 numbers. How many independent parameters here are in this row? So there are 6 numbers. Everyone agrees it's 6 numbers. P of S given yes, P of overcast given yes, P of rainy given yes, and the same thing given no. So 6 parameters. How many independent parameters? What do you know about these numbers? I want someone else to wake up and help me here. Yeah.
I think there's 2, because you know that it has to be one of those 3, and you also know that whether you know that if they didn't play tennis, then they have to not play tennis.
So given yes, given play tennis yes, there are 2 parameters. Because P of sunny given yes, plus P of overcast given yes, plus P of raining given yes, has to be 1. So really, these are not 3 independent parameters. There are 2 independent parameters, and the third one is 1 minus their sum. The same thing happens for no. Right? So again, there are 2 independent parameters for the no. But the 3 numbers of the no and the 3 numbers of the yeses are completely independent, right? They're not related. So really, there are 6 numbers, but there are 4 independent parameters. 2 for the yes case, 2 for the no case. Okay? Again, the reason I'm saying this is just that as a sanity check for us. We want to make sure that we understand what's happening here. The same thing is going to happen for temperature. Again, there are 3 values, high, mild, cool. 2 labels, yes and no, so it's 6 numbers. 4 of them are independent. Same thing for humidity, same thing for wind. So that's what we have to compute. Once you computed all these parameters, you have the ability to predict. So now, given a new instance, here is an example of an instance, you can make a prediction. So let's just do it. So given a new instance, outlook is sunny, temperature is cool, humidity is high, wind is strong, I want to compute. So on the left side, I'm writing, so what I have to do is I have to do argmax, which means I have to compute the probability of yes, the probability of no, and compare them. So on the left side, I'm writing the yes probabilities. So it's the probability of the yes label, 9/14th, the probability of sunny equal given yes, cool given yes, high given yes, strong given yes, and the same thing on the left side here, and then I'm multiplying them. I'm basically following this formula, and I'm getting these two numbers. So what should I do? No, but they do not sum to 1, these probabilities. But why don't they sum to 1? These are probabilities, we think. Or are they probabilities? Right, so remember that when we did the argmax, we left the denominator, right? We said the denominator doesn't matter. So it's not probabilities anymore, it just scales with the probability, but if you really wanted this to sum to 1, you had to carry with you P of x. Or you can just normalize, as I do here, and now you'll get the probability of no given the instance. Okay? Okay, so now what would have happened if I ask you about outlook being overcast? Remember this because I'm going to go back to the data. So look at this example. I'm going to change my example, and I want to predict it in the case that outlook is not sunny, but rather overcast. Let's go back. What would happen if outlook is overcast? Yeah. I don't have a no. So the probability of overcast given yes is 1. The probability of overcast given no is 0. Which means I'm always going to say yes. Whenever I have overcast, it doesn't matter what the other features are, I will never say no, because the product is going to be 0. You see that? So that's a problem. I don't want this to happen. And this is why we are doing what we call smoothing. The way we computed it is nk over n, the number of cases that belong to k divided by the total number. And the problem is that if n is small, or if nk is 0, in both cases we get something that we feel is not right, and we need to be able to smooth. The way we're going to smooth is, there are many ways of smoothing. In the case of naive Bayes, it actually doesn't matter so much how we smooth. All reasonable ways are going to behave well. We're going to do something that is called Laplace smoothing, which I'm defining here. And I'm going to instantiate it here only in the case of the Boolean case, because it's simpler for us. And this is what I'm doing. So it's really going to be, instead of nk over n, nk plus 1 divided by n plus 2. What I instantiated here is the fact that I have two labels, m is equal to 2, and the fact that the two labels are equally likely. So there's a uniform distribution over the labels. Had you wanted to do something else, let's say quarter, 3/4 for the label, you would change the numerator a little bit. It will be, say, nk plus a half, and nk plus 3/2. You can actually try this. But the idea is that you want to push away things from 0, and this is going to do this. Okay, so I think I'm going to stop here, but this will be enough for you to do the problem set. Next time, we're going to move to one new algorithm, the EM algorithm. Okay? Hi.
I wanted to ask you, when you came in today, did you plug this in and then this in here? Or
It doesn't matter.
It does actually.
It doesn't.
Yeah, because that's what Lamont said. That's the reason
He's
that.
wrong.
Okay.
I'm doing this thousands of times. a
Okay,
year.
it's just like a weird glitch sometimes because of
Just-
updates.
Yeah. It's probably.
That's what I would, because that's what I was wondering, like if it was, because he used to be like if he
Yeah,
plugged it in
he
out
can
of order.
experiment with it, and he can see
Okay, and it
doesn't
didn't matter. Okay, that's what I was
I'm
wondering.
doing
about.
this thousands of times in different places. And
No,
this
that's why I
doesn't
was
matter.
wondering. Like, okay,
No,
well,
I think
sorry,
it's just,
sorry for the trouble.
It's just restarting was the right thing to do.
Got it.
It's just that probably it didn't restart it for a few days, and
No worries. There was I wanted to tell you, there's a weird coincidence. I do Airbnb. I rent my guest room out, and I have a data scientist staying with me in 2 weeks. I mentioned that I'm having trouble in your class by name. Turns out her daughter is best friends with her. So Morgan Taylor is her name, and she studied with your daughter apparently. And she said it was her best friend in grad school or something. And she's like,
she actually
it's
graduated
a weird
from here. Right.
coincidence, yeah. So
So
she's
her
staying
mom-
with me in a week and a half.
Morgan's
Morgan,
mom?
Morgan is.
Oh, Morgan is. Oh, wow. Okay.
I just thought you'd think that's
Yeah, yeah,
funny.
yeah.
It was very strange. Like,
She's actually here now, I think, or was here for
well, she'll be
Thanksgiving.
coming here for something in
Yeah.
like a week.
Okay.
Or two. Strange coincidence.
Okay, yeah. Yeah.
You told a group for your office hours, they do like.
Yeah, sure. Yeah.
Right?
Like you do different things.
Yeah, 'cause I mean, yeah, I can understand this time and more.
So why did you ask this in class?
Yeah.
I didn't want to go back to
But that's it.
Comedic understanding.
It's only the end of the semester, and you still. I mean, these are exactly the questions that you should ask in class, because I bet half the students are stuck in the same question. Okay.
So like for the branch, you know, like go
So now, what is
number
the
and like
question?
change the ET and like.
why is that reports for an integer other than, like I would have thought it would have been two.
So if the answer is yes, let's assume the answer is yes. It's blatant. We're conditioning on yes. Then there are three numbers, right? What do you know about these three
I gotta
numbers?
rewatch that, but
What do you know about the three numbers? Alpha equals sunny,
actually not that one. It's a
given
different
yes, alpha given overcast given yes, alpha given anything. What do you know about these three numbers?
Oh, yeah.
And no, don't confuse them. Just give me something you know about it. Condition.
It was
about
good.
it. The sum of two, which means two of them are independent, and the third one
Preparation
depends
for the
on
next 2
that,
weeks of hell.
right?
Oh, you're new to that. You know, like you're cherry hill.
Now let's move to the no.
Oh, nice.
Let's condition on the no. Again, you have three numbers.
Yeah.
You have sunny given no, overcast given no, rainy given no.
Really there? It was just raining. The one day I went last year by
These
complete
three
accident,
numbers.
in Arizona.
supervised, or two of them.
Yeah.
Independent, the
I see,
third
I want
one,
like every,
it has to be one minus something. Now, let's think about overcast given yes, and overcast given no. Okay?
you would like Aaron State.
Are
That's
they
my
related?
Okay, I'll switch in there.
No.
Although there's actually a
So
better
the three numbers given the yes are completely independent than the three numbers given the no. Right? It could be that, given yes, it's always
I would say
overcast,
figure out
given no, it's never overcast. These things are never related. So,
Oh, you never
so
wrote
really,
that?
you have
I purposely chose
three
to that was
sets of numbers. Given the
Oh,
yes,
okay. So I took the Amtrak
given the
in.
no.
Or no, I took a mega bus in, so it drops you off like on the station.
Independently, these
And so to get from there to the mall,
these
you
three
walk
things some to one.
here.
But there are no relation between them. So altogether, you form independent numbers.
Yeah, it's like it's a
subtracting. Yeah. That makes sense. But that thing works with
Okay, next time ask it in class. It's really, I'm waiting for questions. No one asks questions, which means it's trivial, but then it turns out it's not trivial.
All right. Thank you.
Okay?
So we actually are a team for the project, but we haven't met yet.
So come to my office.
Can we do it tonight?
Yes?
Unfortunately, we've got until 5:50. Could we meet at maybe 6?
Come as soon as you feel.
Very good.
Thank you.